All right, let's look at some of the awesome things about water that makes it so unique and so important and just so darn cool on our lovely planet here. Perhaps, as Raoul said, planet ocean, not planet Earth. But remember that water is the foundation of all living things. Yay for water, yay for life on our planet. And a lot of the uniqueness of water comes because of what's going on in the molecule. So again, at the particle level that we like to look at a bunch of different things. Within the water molecule, between the hydrogen and oxygens, we have polar covalent bonds. And if we remember, that means that oxygen is more electronegative, pulling the electron from hydrogen closer to it. So we end up with poles on the molecule. We have a partial negative part of the molecule, which is where oxygen is, partial positive pole on the molecule where the hydrogens are. Now, because of oxygen's lone pairs, it ends up having a bent shape as a molecule, and so because of that bent shape, the dipoles don't cancel out. Water is, in fact, a polar molecule. Then, because of that, in a sample of water, we end up having all of these hydrogen bonds. And again, a hydrogen bond, the partially positive hydrogen of one water molecule, is attracted to the partially negative part of the oxygen on another water molecule, and that attraction is a hydrogen bond. So you can see all where the yellow arrows are, all the different hydrogen bonds between those different water molecules. And because of these hydrogen bonds, again, we get all of the different unique properties of water. And so, like listed in the packet, high surface tension, low vapor pressure, high boiling point, high heat of vaporization, high specific heat, the fact that the solid form floats in the liquid form, and that water can dissolve so many substances. And as it says there, one of water's oddest traits is that it's a liquid at room temperature compared to many other molecules that are gases. And again, other molecules like methane, ammonia, carbon dioxide, oxygen, nitrogen, they do not experience that hydrogen bonding, and so they readily become gases at room temperature, whereas water stays a liquid. All right. Now, looking at a sample of water, those particles in the middle of the liquid, as it says they're the bulk of the liquid, they're pulled in all directions. And you can see that here in this enlarged view. And those are the hydrogen bonds that are pulling those molecules in all directions. Now at the surface, though, not so much. At the surface, the air does not pull the water molecules. So those water molecules are only pulled downward, inward. And that's when we end up having that surface tension. And so we can look at surface tension. As I mentioned in the packet, have you ever gone off a diving board and experienced a belly flop? And if you have done that, it can kind of hurt. That water is like a skin. I mean, it definitely has a smacking feel to it when you hit the water inappropriately. Here we have this lovely show. I don't know if you saw it the other night. It's called Splash on ABC. Let me show you a little snippet from that.
Splash, the stars will fall.
You could almost feel that tension as you saw that person coming closer to the water, knowing how much that might hurt when you smack in that fashion. This is also why we can see these water walking bugs. They are so light and their surface area of their feet are spread out enough so that they can actually walk on this surface of the water. And again, it looks like there's a film, a skin on top of the surface. And again, on plants or on cars, you can see that, on a freshly waxed surface, that the water beads up. And you can see that in these diagrams, the fact that on the surface at the top of the bubble, those molecules are only attracted inward and pulled in, and so that's why we have this beading formation. Now, if a liquid turns to a gas below the boiling point, that's what we call evaporation, and water does not do that very often. It has a very low vapor pressure, and vapor pressure, of course, is when uh, liquid molecules escape and become a gas and collide with the air above it. And so more molecules that escape will create more pressure because there's going to be more collisions with the air molecules above the surface of the liquid. Less molecules that escape, less vapor pressure, less collisions. And so water, with its hydrogen bonds, those molecules don't escape as easily. And so water has a low volatility, okay? Volatility, sorry. Low vapor pressure. If a liquid evaporates very quickly, then it is what we call volatile, high volatility, and a high vapor pressure. Like acetone and a lot of chemicals that have a very strong smell because those liquids are evaporating so quickly and you can smell that real quick. Even nail polish remover that doesn't use acetone anymore, it still has a substance in there uh, that I had in your packet. And sorry, I'm looking for it right. Acetonitrile, that's what I thought. Acetonitrile, and it still is very volatile, and you can sense that as through the smell, etc. And I'll talk about the coolness factor in a moment. Now, when the vapor pressure of a liquid equals the atmospheric pressure above it, that's when boiling starts to happen. And again, water has a very high boiling point, and so there's not many particles escaping into the liquid phase. You have to heat it up, heat it up, heat it up to break those hydrogen bonds until finally we see the bubbles pass through the liquid, and that is the boiling that is occurring. Now, boiling is sensitive to atmospheric pressure, obviously, because you have to get the vapor pressure to equal the atmospheric pressure. As we talked about before, the higher you go up in elevation, the lower the atmospheric pressure. There's less molecules up there, less oxygen in the atmosphere, so there's less collisions, less pressure. So like in Denver, the mile-high city, the water there actually boils at about 95 degrees Celsius, lower than 100, which is what it boils at sea level. And so we actually see high altitude directions, and here we see a high altitude cookbook. And that's happening because, with the lower boiling point, we sometimes have to increase the time. It doesn't matter what temperature you turn the oven to, the water's still going to boil at 95 degrees Celsius, which is about, I'd say about 205 degrees Fahrenheit compared to 212 normally. And sometimes you might have to add a little more water as well, just because you have to increase the cooking time to keep the food more moist. Now, the reverse of vaporization is called condensing. And so when you're heating something up like in the microwave, as it mentions in the packet, if you open up that container very quickly, that steam coming out at you has very high energy, and if it hits your skin, it condenses and turns back to a liquid, releasing all of the energy that it has trapped in it. And so you can get some very serious consequences if you let that steam blast you on your skin. So be very wary of that. Now, just mentioning real quickly, I believe it's question 13 again. Why do you feel cold when a volatile liquid contacts your skin? If you've ever gotten fingernail polish remover or paint thinner, it feels cold because it evaporates so quickly and it takes the heat away from your skin, so you have that cold sensation. Just want to make sure that you got that answer if you were looking for that for number 13. So now we're on specific heat. Okay, and again, specific heat is how much energy it takes to change 1 gram of a substance 1 degree Celsius. All right, and water has a very, very high specific heat. It can absorb a lot of energy before its temperature changes, unlike most other substances. For example, metals or even sand. So that's why it says, you know, if you walk on the sand at the beach on a very hot sunny day, it's pretty hot and it can actually burn your feet. But the water, if you make it to the water right there on the shore, it's much cooler, even though it's being exposed to the same sunlight, the same energy that the sand was. Its temperature changes a lot less. And so we can calculate using specific heat, we can calculate how much energy is absorbed by a substance or how much energy is released by a substance depending on, you know, how the temperature is changing. So here we had a question that said, if you have 256 grams of each of these substances, water, iron, and sand, how much energy is it going to take to heat the samples from 20 degrees Celsius to 99 degrees Celsius? So what this depends on are the specific heats. So water, again, water specific heat is 4.184. That's C. The mass, I said, for each of these, we're going to use 256 grams. And then the change in temperature from 20 to 99, that is 79 degrees. All right. Iron, its specific heat is 0.444. And again, we're using 256 grams and a change of temperature 79 degrees. Sand, its specific heat is 0.703, and again, 256 and 79. Multiplying those out, and I'm just going to round to the nearest whole number, which is fine for now. So I see that the water, it's going to take 84,617 joules, whereas the iron is only going to take 8,979 joules, and the sand's kind of in between, but closer to iron, 14,217 joules. So you can see, same amount of substance, same temperature change, takes a heck of a lot more energy to do that to water than it does to the iron or to the sand. And we use the same equation if we're going to cool a substance down. Okay, how much energy is released when we have 875 grams of copper and 875 grams of water cooled down from 92 to 25. All right, so for copper, specific heat of 0.385, and again, we have 875 grams, and the delta T 92 to 25 is 67. Even though we're cooling down, it's still just the change in temperature. So again, water 4.184, the mass 875, and the delta T of 67 is the same. And again, when we calculate, copper, 22,570 joules are going to be released. Water, 245,287 joules. Big, 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 big difference. All right. And then our last calculation here that we can do is we could actually calculate the specific heat of something, rearranging that equation. So here we have a piece of metal, heating it up, initial temperature, later temperature, and how much energy is absorbed. So what is the specific heat? So to find the specific heat, I need the Q, which is 73,280 joules, and then I divide that by the mass, 722, and the change in temperature, 249 and 23, that is a difference of 226. Do the math correctly, and when you do, the top divided by the bottom, we're going to get 0.449. Technically that's joules per gram degree Celsius, but and then you can look up that specific heat, like on the back of your periodic table. I was going for chromium, but looking on the back of your periodic table, iron also has that specific heat, even though I had 0.449 or 0.444 in the packet. Just depends on which chart you're looking at. All right, so that's the first part of this water stuff. Hope this helped.